Main sequence stars fuse hydrogen atoms to form helium atoms in their cores. About 90% of the stars in the universe, including the Sun, are main sequence stars. These stars can range from about a tenth of the mass of the Sun to up to 200 times as massive. Over a star's life, the outward pressure of fusion has balanced against the inward pressure of gravity. Eventually, a main sequence star burns through the hydrogen in its core, reaching the end of its life cycle. At this point, it leaves the main sequence. Once the fusion stops, gravity takes the lead and compresses the star smaller and tighter. So the core begins to contract due to its own gravity. This brings additional hydrogen into a zone where the temperature and pressure are sufficient to cause fusion to resume in a shell around the core. The hydrogen-burning shell results in a situation that has been described as the Mira principle. When the core within the shell contracts, the layers of the star outside the shell must expand. The core contracts and heats up due to the lack of fusion, and so the outer layers of the star expand greatly, absorbing most of the extra energy from shell fusion. This process of cooling and expanding is the subgiant star. The increasing core temperature results in an increasing luminosity, while the resulting radiation pressure from the shell burning causes the outer diffuse envelope of the star to expand to hundreds of solar radii, hence the name, giant. Stars spend approximately a few thousand to 1 billion years as a red giant. Eventually, the helium in the core runs out and fusion stops. The star shrinks again until a new helium shell reaches the core. When the helium ignites, the outer layers of the star are blown off in huge clouds of gas and dust known as planetary nebulae. These shells are much larger and fainter than their parent stars. The core then continues to collapse in on itself. Smaller stars such as the Sun size end their lives as compact white dwarfs. We explore some of such red giant stars observed that potentially will end up as white dwarfs. The material of larger, more massive stars fall inward until the star eventually becomes a supernova, blowing off gas and dust in a dramatic fiery death. Theoretical studies indicate that most supernovae are triggered by one of two basic mechanisms: the sudden reignition of nuclear fusion in a degenerate star such as a white dwarf, or the sudden gravitational collapse of a massive star's core.
Aldebaran is the brightest star in Taurus and generally the 14th brightest star in the night sky. It is about 65 light-years away. Aldebaran is a giant star, cooler than the Sun with a surface temperature of 3,900 K, but its radius is about 44 times the Sun's, so it is over 400 times as luminous. Its spectrum shows that it is a giant star that has evolved off the main sequence after exhausting the hydrogen at its core. The collapse of the center of the star into a degenerate helium core has ignited a shell of hydrogen outside the core and is now on the red giant branch. Aldebaran will reach about 800 solar luminosities within the next few million years. Eventually, it will lose much of its current mass through its strong stellar wind and expel its outer envelope to form a planetary nebula, leaving behind a white dwarf.
Gacrux is the nearest Class M giant star to the Sun. It is the third brightest star in the southern constellation of Crux and is listed 26th of the brightest stars in the night sky. It has evolved off of the main sequence to become a red giant star, but is most likely on the red giant branch rather than the asymptotic giant branch. Although only 30% more massive than the Sun, at this stage the star has expanded to 120 times the Sun's radius. It is radiating roughly 760 times the luminosity of the Sun from its expanded outer envelope. With an effective temperature of 3,689 K, the color of Gacrux is a prominent reddish-orange. Eventually, it will die as a white dwarf.
Hamal is the brightest star in the northern zodiacal constellation of Aries. Based upon parallax measurements made with the Hipparcos astrometry satellite, Hamal is about 65.8 light-years from Earth. It is a giant star that may host an orbiting planet with a mass greater than Jupiter. It is an evolved giant star that has exhausted the supply of hydrogen at its core and is now on the red giant branch. Hamal is radiating about 91 times the Sun's luminosity from its outer envelope at an effective temperature of 4,480 K. This is cooler than the surface of the Sun, giving it the orange-hued glow of a K-type star. In only a billion years or so, big old Hamal will shrivel up into a tiny white dwarf.
Kappa Persei is a triple star system in the northern constellation of Perseus. Based upon an annual parallax shift of 28.93 mass, it is located at a distance of 113 light-years from the Sun. With an estimated age of 4.58 billion years, Kappa Persei RR is an evolved G-type giant star with a stellar classification of G9.5 IIIB. It is a red clump giant, which means that it is generating energy at its core through the nuclear fusion of helium. The star has about 1.5 times the mass of the Sun and 9 times the Sun's radius. It radiates 40 times the solar luminosity from its outer atmosphere at an effective temperature of 4,857 K.
Delta Andromedae is a multiple star system in the northern constellation of Andromeda. Based upon parallax measurements, it is located at a distance of approximately 105.5 light-years from the Earth. The primary of the spectroscopic binary has a stellar classification of K33, indicating that it is a giant star. It most likely evolved from a F-type main sequence star after consuming the hydrogen at its core. The secondary is a relatively faint K-type dwarf, which has been imaged using a stellar coronagraph. Delta Andromedae estimated radius has been calculated as being 10.63 times bigger than the Sun.
Mira is a red giant star estimated to be 200 to 400 light-years from the Sun in the constellation Cetus. This binary star system consists of a red giant Mira A undergoing mass loss, and a high-temperature white dwarf companion, called Mira B, that is accreting mass from the primary. Ultraviolet studies of Mira by NASA's Galaxy Evolution Explorer Space Telescope have revealed that it sheds a trail of material from the outer envelope, leaving a tail 13 light-years in length, formed over tens of thousands of years. It is thought that a hot bow wave of compressed plasma gas is the cause of the tail.
Alpha Herculis, also designated 64 Herculis, is a multiple star system in the constellation of Hercules. Based on parallax measurements obtained during the Hipparcos mission, it is approximately 360 light-years distant from the Sun. Alpha Herculis A has been specified as a standard star for the spectral class M5 Ib2. Like most Type M stars near the end of their lives, Alpha Herculis is experiencing a high degree of stellar mass loss, creating a sparse gaseous envelope that extends at least 930 astronomical units. If Alpha Herculis were at the center of the solar system, its radius would extend past the orbit of Mars at 1.5 astronomical units, but not quite as far as the asteroid belt. The red giant is estimated to have started its life with about 3 times of our Sun.
IK-Pegasi is a binary star system in the constellation Pegasus. It is just luminous enough to be seen with the unaided eye, at a distance of about 154 light-years from the Solar System. IK-Pegasi b is the nearest known supernova progenitor candidate, when the primary begins to evolve into a red giant. It is expected to grow to a radius where the white dwarf can accrete matter from the expanded gaseous envelope. When the white dwarf approaches the Chandrasekhar limit of 1.4 solar masses, it may explode as a Type Ia supernova.
Spica is located about 250 light-years from the Sun. The luminosity class matches the spectrum of a star that is midway between a subgiant and a giant star, and it is no longer a main sequence star. The evolutionary stage has been calculated to be near or slightly past the end of the main sequence phase. This is a massive star with more than 10 times the mass of the Sun and 7 times the Sun's radius. The bolometric luminosity of the primary is about 20,500 times that of the Sun, and 9 times the luminosity of its companion. The primary is one of the nearest stars to the Sun that has enough mass to end its life in a Type II supernova explosion.
Alpha Lupi is a blue giant star. It is around 460 light-years from the Solar System. It is one of the nearest supernova candidates. It is a giant star with about 10 times the mass of the Sun, yet is radiating 25,000 times the Sun's luminosity. The outer atmosphere has an effective temperature of 21,820 K, which gives it the blue-white glow of a B-type star. It's already at the end of its normal lifetime. Eventually, the star is likely to explode as a supernova.
Antares is a red supergiant star, approximately 550 light-years from the Sun. The brightness of Antares at visual wavelengths is about 10,000 times that of the Sun. But because the star radiates a considerable part of its energy in the infrared part of the spectrum, the true bolometric luminosity is around 100,000 times that of the Sun. The mass of the star has been calculated to be about 12 times of Sun. Comparison of the effective temperature and luminosity of Antares to theoretical evolutionary tracks for massive stars suggest a progenitor mass of 17 times of Sun, and, like the similarly sized red supergiant Betelgeuse in the constellation Orion, will almost certainly explode as a supernova. For a few months, its supernova could be as bright as the full moon and be visible in daytime.
Coronae Borealis is a binary system containing a large cool component and a smaller hot component. The cool component is a red giant which is transferring material to the hot component. The hot component is a white dwarf surrounded by an accretion disk, all hidden inside a dense cloud of material from the red giant. When the system is quiescent, the red giant dominates the visible light output and the system appears as an M3 giant. The hot component contributes some emission and dominates the ultraviolet output. During outbursts, the transfer of material to the hot component increases greatly, the hot component expands, and the luminosity of the system increases. The accreted matter could push the white dwarf over the fabled 1.4 solar mass limit, beyond which it would collapse and blow up in a grand supernova that even at a distance of 2,500 light-years could become as bright as a crescent moon.
Rho Cassiopeia is a yellow hypergiant star in the constellation Cassiopeia. It is about 3,400 light-years from Earth, yet can still be seen by the naked eye as it is over 300,000 times brighter than the Sun. Its diameter measures between 400 and 500 times that of the Sun. Rho Cassiopeia is a single star, and one of the rarest types of stars. Only a few dozen are known in the Milky Way. It's getting near the end of its life. Not long ago, it most likely was a red supergiant, so it was even bigger than it is now. And eventually, it'll blow itself apart as a supernova. Its outer layers will blast into space, while its core will be crushed to form either a super-dense neutron star or an even denser black hole.
Despite being one of the most luminous stars known, 500,000 times brighter than the Sun, IRC +10420 cannot be seen with the naked eye and needs a telescope to be observed. Models suggest it started its life as a 40 to 50 solar masses star that lost most of its mass due to strong stellar winds, leaving it with just 10 solar masses. Evolutionary predictions for the physical properties of supernova progenitors derived from approximately 18 to 20 solar mass stars that have experienced enhanced mass loss is red supergiants.
Mu Cephei is a red supergiant or hypergiant star in the constellation Cepheus. It is visually nearly 100,000 times brighter than the Sun. It is also one of the largest known stars with a radius around or over 1,000 times that of the Sun, and were it placed in the Sun's position it would engulf the orbit of Mars and Jupiter. Mu Cephei is nearing death. It has begun to fuse helium into carbon, whereas a main sequence star fuses hydrogen into helium. When a supergiant star has converted elements in its core to iron, the core collapses to produce a supernova and the star is destroyed, leaving behind a vast gaseous cloud and a small, dense remnant. For a star as massive as Mu Cephei, the remnant is likely to be a black hole.